start. Good morning, good afternoon, and good evening, everyone. Welcome to the 11th episode of season 3 of the Young Researchers Forum on Detonation. Today we have our speaker, Dr. Eric Bach from TU Berlin in Germany. And Eric is currently a postdoc researcher at TU Berlin, and he's also a part of the chair of a pressure gain combustion under Professor Miles Bohon, who was also a speaker of the previous season of the forum. And his work is right now focusing on RDE performance characterization and gas turbine integration. Eric received his diploma in mechanical engineering from TU Dresden and his PhD from TU Berlin. He has been involved with RDE research since 2018 and is part of the AIAA pressure gain combustion technical committee. Prior to his doctoral work, Dr. Bach focused on research related to high-frequency combustion dynamics and the liquid fuels in gas turbines with industrial partners such as the GE Power, Rolls-Royce, and MTU Aero Engines, and the main energy solutions. And today we will listen to his talk about the RDE performance characterization towards gas turbine integration. So Eric, the floor is yours, please.
Thank you. Let me try to share my screen.
Yeah.
So I hope everyone can see and hear me and my slides, my presentation. If not, it's an especially dark and rainy Friday in Berlin. So yeah, I don't know if the light goes out. Let me know. So we can all enjoy this presentation together. Yeah. Hello and welcome from my side as well. Good afternoon, good morning, good evening. Thank you for joining me. It looks like we have quite a nice crowd. I'll try to make this Friday a bit more interesting with my presentation on RDE performance characterization and yeah, first steps towards gas turbine integration. So as has been said, I'm Eric. I'm working at TU Berlin currently as a postdoc. I graduated last year, also on RDE research. I have been involved in pressure gain combustion research since about 2018. And today I'm going to talk about some of the results that came out of my PhD placement here in Berlin. So let's see if this works. Yeah. So to kind of set the tone with this motivational slide, of course, today we're looking at gas turbine integration of RDEs. And the reason why we want to do that is quite nicely summarized in the plot on the right. So looking at different gas turbine architectures, be it in an industrial or a power generation environment, like this example here from Siemens, or an aviation engine, aviation gas turbine like this Rolls-Royce gas turbine. We are now using, of course, the conventional constant pressure heat addition process, and that is, or performance increases, efficiency increases with these conventional methods are usually tied to an increase in the turbine inlet or the firing temperature. And over the past decades, this, of course, has resulted in quite tremendous efficiency levels of high 50 to low 60% values. Now, switching to a constant volume or detonation heat addition process is quite attractive for this kind of environment, as it would allow a step change in efficiency without the need to significantly increase the turbine inlet temperature, or even have a sizable efficiency increase at quite a moderate to low turbine inlet temperature. This, of course, relates back to not only the pressure increase across the combustion process that is associated with these constant volume heat addition steps, but also the lower entropy generation that is occurring in the heat addition step of the thermodynamic cycle. So comparing these different cycles, this becomes quite obvious. Now, a rotating detonation engine, if any one of you does not already know, is quite a simple device that is just an annular combustion chamber. So just two concentric cylinders forming an annular channel, and at the head end, unreacted fresh gas, fresh mixture is introduced, and then once ignited, a detonation wave will propagate circumferentially around the annular channel for as long as new reactants are provided. Then the high enthalpy gas leaves the chamber at the aft end, and the properties of this high enthalpy gas, they vary quite significantly with a frequency that is associated with the propagational velocity of the detonation wave. It can be in the a few to several kilohertz range. What is so attractive about this concept is that it allows us to decouple a nominally subsonic axial flow, which would go from bottom to top here in this animation, with the high supersonic detonation wave that travels at Mach 4 or 5. And that is, of course, very conducive to our idea to integrate detonator feed addition with a gas turbine engine that usually requires not a high subsonic flow. Here at TU Berlin, just to kind of introduce ourselves and me, RDE research started in 2016 with a grant from the Einstein Foundation, and at the time in collaboration also, or close collaboration with the University of Cincinnati. And the program then grew from there. We have also been involved in the German Federal Aviation Research Program through the German Department of Energy. And since 2021, we are also part of an EU, I always mix these up. It's either innovative training network or a European training network, something like that, where we collaborate with a whole number of research organizations across all of Europe, training, I think, more than 15 PhD students. So our efforts and our group has grown quite considerably in these just few years. So now we can get to more detailed, more granular view of the whole field of the whole topic. As I said, the properties of the exit flow that we want to use in our gas turbine, they vary due to the RDE's particular nature and the kilohertz range, and also with significant amplitude. And that is not very conducive to a turbine architecture. It's not very benign for vanes and blades that are in the hot gas path. And it's also not very easy to simply determine the properties at the appropriate sampling frequency and detail. And this is what my PhD really has been looking at, to quantify the actual stagnation pressure that we obtain from the exit flow of an RDE and how that compares with different designs across different operational parameters. Now, the stagnation pressure gain of an RDE is typically defined as the ratio of stagnation pressure of the exit throat, which is the station 8 in this little comic here, to that of the reactant planner. We are mainly focusing on air breathing applications, so we are for now only comparing the exit throat stagnation pressure to the air plenum stagnation pressure. Now, it's quite easy to determine the stagnation pressure in the air plenum. You simply put a pressure sensor at a location where flow velocity is negligible or the Mach number is negligible, and then a simple static pressure measurement suffices, and you can directly back out PT2. Now, PT8, this is where it gets really tricky. PT8. Not only do you need to be able to measure that, but also to appropriately average that measurement. Currently, there are 3 main approaches to tackling that. The first is using a static pressure measurement. The second is using a thrust measurement. And then our approach has been mainly focused on direct measurements using flow probes that are placed in the hot gas path, as shown in this picture here. And now we're going to step through all of these individually and look at the advantages, disadvantages, and then try to compare all of them. So we start with the Mach-corrected CTAP method, as it is called, sometimes also referred to as the NPS method. That's the Naval Postgraduate School. And this is based on what is called a CTAP. So a CTAP is a capillary tube averaged pressure probe. It's just a port in the combustor wall that connects through a long capillary to a pressure sensor. Now, the idea is we place this CTAP at a location in the post-flame region, so downstream of the detonation wave. And then we measure the static pressure there. And using our area Mach number relation, which we of course define as designers of the RDC, we can back out the Mach number at this exact location where we measure the static pressure. So M4 would refer to the Mach number at this position. And then using that Mach number, we can simply convert the measured static pressure to a total or stagnation pressure, which is PT4 here. Now, if you get confused about all these numbering of the stations, this is now quite common way to define these individual positions here and summarize in this table. So station 2 refers to the reactant planner. 3.1 is the injector throat area. 3.2, this would be around here where the detonation wave is propagating. And 4 is the post-flame region, but still inside the combustor. And station 8 is the combustor exit throat, so the exit plane of the channel here. What, of course, we need to do for this method is we need to assume that the throat is flow at the throat is choked, so there's a sonic condition at the exit plane. Only then can we use the area Mach number relation to back out the Mach number at station 4. In comparison to that, the EAP method revolves around measuring thrust of the high enthalpy jet that exits the combustor. And EAP is what is called equivalent available pressure. This concept was introduced in about 2018, I think, by Tom Camming and Dan Paxson, and it's sort of a measure of the stagnation pressure of this very unsteady flow that is similar or equal to that of a steady flow device, providing the same level of thrust. Now, it works in a way that we take the general thrust equation, so we take our measured thrust and rearrange that for the static pressure at the exit plane again. Now, assuming once again that the flow is choked at the exit throat, we can quite simply, using our measured thrust, convert that to an averaged static pressure at location 8. And from that, again, we can back out the total pressure or EAP. What needs to be mentioned here is that the measured thrust or the gross thrust that is the input for this equation is has two constituents. So this is the net thrust that is actually measured by the load cell when we turn on the device and it is firing. And the second term here, FBD, this refers to the base drag of the device. So as you can imagine, once you have that high entropy, high flow, high velocity jet exiting the chamber, I'm sorry, this will pull a vacuum on these flat surfaces here and induce a base drag. And you actually need to be able to account for that and include it in your calculation. Otherwise, you're missing quite a sizable chunk of the thrust, of the force. So recently, we've been attempting to also design and set up our own thrust stand. We're going to look at some example data later, but this is just as an introduction here. It's a movable sled type thrust stand. So we have a fixed frame and the RDC then connected to a sort of sliding frame. The two frames are themselves connected through a S-type load cell, as you can see here. We have a pair of springs that we use to apply a preload to this load cell and just a simple rubber damping element that attenuates the characteristics, so the impulse response characteristics of this stiff system. We do every couple of runs, we do a calibration of our load cell, of the whole stand actually. For that, we use a screw jack connected to a reference load cell, and we just apply a reference force. And as I said, we also included a base drag measurement system. So this is really just a number of pressure ports on the center, both on the center body and on the outer flange, distributed radially, so at different radial positions. And with, we're going to look at some examples just in a minute, but yeah, this allows us then to really determine the pressure distribution across these surfaces. Now, finally, our method that we have been so far using mainly, this is the direct keel probe method, and for that we use additively manufactured keel probes. So a keel probe is really just a pitot probe with an aerodynamically shaped shroud that redirects the flow in such a way that it always arrives perpendicular to the main axis of the pitot inlet. And we really just place these flow probes right in the hot gas path and measure the response of a pressure sensor that is attached through a thin capillary. Of course, introducing a probe directly into the flow can result in a bow shock forming in a supersonic environment. So this would again induce a pressure loss. So you would not really measure the actual stagnation pressure, but through the flow processing through this shock would have a slightly decreased stagnation pressure. Also, at the exit plane, the flow angle is still oscillating quite a bit, so you need to be able to incorporate to account for that in your probe design. The keel shroud needs to be designed in a certain way. And then, of course, there's an internal capillary that connects the pitot head here with the pressure probe at a further position, and this will have a frequency response as well. So there's quite a number of ways you can induce an error in your measurement here, but you can really place this probe wherever you want, and you don't need to have this sonic assumption that is associated with the other two methods. And of course, you need to be able to design a probe that lasts sufficiently long to not melt away or fly away when you do that measurement. So really what we're interested in is if we are actually comparing apples to apples when we look at these three methods and the stagnation pressure that we back out from each one. And this plot is summarized quite bluntly published data for the stagnation pressure gain of different RDEs. And now these really do include, of course, a really very wide combustor design space. So not all of these are air breathing type designs. Some are rocket type devices using all sorts of different fuels, all sorts of injector designs. So it's, although it seems at first that really the results all fall in one line, this does oversimplify the whole issue quite a bit. And there are a number of dimensions folded into this view that are important for pressure gain, but are omitted here. So maybe I should have mentioned that we have on the vertical axis the stagnation pressure gain, so this ratio of PT8 over PT2, and on the horizontal axis is the area ratio of the exit throat to the oxidizer injector throat. And yeah, it's not easy to really pull all of this data from the published literature. A lot of times there's underreported data, especially for the EAP method. You need to take into account so many parameters that this can be overlooked quite easily, that not all of it is reported in any given paper. And then there's different averaging methods baked into that. So really what we are interested in is having one combustor, one test rig, where we can look at all three methods and then decide, okay, we are able to use the Kiel-Probe method for some regions of this parameter design space. And in some cases, we do need the EAP method. How do they compare? What are their benefits and disadvantages? So now we can look at some examples. This is a typical output from our Kiel-Probe here on the left. We have on the leftmost side, just prior to the ignition, we have pressure induced from just the flow of cold reactants. And then after the ignition event, we quite nicely see the internal capillary pressurizing for some time, and then plateauing at a certain any given value that is associated with this operating point, with this design point of our RDC. What we then usually do is we take just the last 50 milliseconds of this time trace, and we average that, and we'll assign this value as our average stagnation pressure at the exit throat. And we can do this for a whole range of operating conditions and combustor designs. And this is summarized here on the right, and we can quite nicely see that we can influence the pressure gain and the stagnation pressure. So this plot here shows the PT8 value, and this plot shows the ratio, so the pressure gain, PT8 over PT2. And so the first thing we notice is that, of course, if we increase our mass flux, so the horizontal axis here is mass flux at the throat. This is the mass flow passing through the throat area, so J8. We can see, of course, increasing the mass flux will result in a higher stagnation pressure. And also these markers here are color-coded by the outlet restriction. So that is the area ratio of the exit throat to the annulus, the combustion annulus, A8 to A3.2. And we go from fully open, these would be the red circular markers, to 50% restricted. These are the orange triangles. And we can see that, okay, increasing or having a larger restriction or more restrictive outlet does also result in increased stagnation pressure gain. What we typically see is that first we have a negative slope here, so we decrease in pressure gain, and this is associated with the exit throat slowly becoming choked. So then at about, let's say, 200 kilogram per second and square meter, we establish a sonic condition at the exit throat, and then we go with a positive slope, we increase the stagnation pressure gain. Similarly, the Mach-corrected CTAP looks quite identical, actually. So again, we have, after the ignition event, the capillary quickly pressurizing and reaching a sort of steady value. Of course, the capillary design or capillary geometry is not able to really dampen out all of these high frequency fluctuations. So you always have some higher frequency content in the signal. And typically we do the same thing here. We use just a temporal average of the last 50 milliseconds of this time trace to back out the static pressure and then convert it to a total pressure. Now what we can see here is that there's also a bunch of unfilled markers, or these white markers here, and these are associated with an outlet pressure that is below the atmospheric pressure, below the critical pressure ratio, where the assumption of a choked outlet is not satisfied anymore. And for that, we can actually do some correction, but our measurement method would break down here. So it would not, as is, would not provide really reliable data in these regions. But overall, we see the same trends, of course. We can increase the stagnation pressure gain quite nicely with increasing either the mass flow or restricting the outlet more. Now for our EAP measurements, these usually come in two parts. So the first is the thrust that we measure with our load cell, of course, and here you can quite nicely see the damping characteristic of the system. And I admit there might be some fine-tuning necessary. We have a very modular design where we can replace all of these individual components, and this is what we actually do. So for each run, we choose a certain set of preload or damping coefficients to get to a sort of steady level quite quickly. So we have the thrust value, and then on this plot, we also have the output from our base track sensors. So this group here, the lower group, these are sensors located on the center body. And these three lines, these correspond to sensors located on the outer flange. And we can see that actually on the center body, there's quite a significant decrease, so quite a significant vacuum that we then multiply with the area that is associated with each of these sensor locations. And then we kind of integrate over the whole pressure distribution to get the full base drag value, of course. And here we similarly have then these markers where the calculated pressure is below the critical pressure ratio, and we have to do some additional steps to account for that. But as is, would not satisfy the choke flow condition or assumption and does not provide reliable data. But there's a way around it, and we can provide a low Mach number correction. The way this is done usually is to assume that the static pressure at the throat corresponds to the ambient pressure. And of course, we want to calculate from that our total pressure at the throat. For the CTAP method, we kind of have to iterate between these two equations. So we have to use the area Mach number relation in conjunction with the pressure Mach number relation. And then using this assumption, you kind of iterate long enough until you get to a certain value for the Mach number at station 4 that then satisfies this assumption. For the EAP method, it's a little more straightforward. We can directly put in this pH value. So using here the ambient pressure and our measured thrust, we can back out the Mach number at the exit throat. And using this correction, we can then apply that to our data and actually get sensible values even at these low flow conditions. Now, in the end, what we get out for our preliminary initial data set is a relation between these three different methods. So on the right, we have PT8 measured with our kill probe compared to PT8 measured through the EAP method. And similarly, we have PT4 from our CTAP compared to PT8 from EAP. And this is done for a whole range of operating conditions, so different mass flow values and a whole range of design, combustor design conditions. So here we have outlet restrictions going from fully open to about 50% restricted, and also across different air injectors with area ratios from very high or very stiff injector at 0.144 to quite an open injector at 0.46. And we see that even in this initial data set, we do actually have quite a good agreement between the individual methods, and we are not so far off the one-to-one line. So really emphasizing that there is, well, not perfect agreement, but we're also still working on some fine-tuning, some details of our setups. But regarding or considering that both the kill probe method and the CTAP method really drastically reduce the amount of necessary instrumentation and are quite easily implemented into any given setup. These are quite attractive ways of determining or estimating the stagnation pressure and the stagnation pressure gain in an RDE device. What we then did in the next step was to provide a large database of stagnation pressure measurements from our keel probe. And our combustor is kind of modular in a way that we can very easily swap out the center body exit plate here and just implement different outlet restrictions. And also by just switching out this spacer plate, we can adjust the air injector stiffness. And what we did is we went ahead, put our keel probe at its location, and then went through a whole range of operating conditions and design points to just provide a large database. And I know there's a lot going on this slide, but I'm gonna point out just the most important parts. So this is more or less all of our data for all of the configurations that we have available. And going horizontally from left to right, these individual plots are for different air injectors. So they are distinguished by the air injector area ratio. We go from a very stiff injector to a very open injector on the right. And similarly, on the vertical axis, we have the outlet restriction, where we go here from fully open down to about 50% restriction. And now these markers are again color-coded, but this time by the operating mode that we observe in the combustor. So go from, let's say, this clapping mode with 2 counter-rotating waves to more canonical cases where we have a very dominant single wave, maybe with some counter-rotating components or just the single wave processing in the combustor. And then also to more kind of chaotic operations with multiple co- and counter-rotating waves. And really what I want to emphasize is that as we approach these configurations where positive pressure gain is more likely, so low air injector stiffness, increased outlet restriction, we really narrow down this area where the combustor is happily operating with the single wave case. And this actually we identified as a large challenge, or I guess most research groups identified this as a large challenge, that these conditions where you really could reap the benefits and create a positive pressure gain, these tend to be associated also with these increased loss mechanisms that take away some of the energy from the detonation wave, and not all of the fuel is really processed in this nicely behaving single or co-rotating detonation wave. Now plotting these data again, a little bit differently this time. Again, we have the 4 plots for our air injectors. And really here we put just the stagnation pressure gain, color-coded by the outlet restriction as well. And from plotting it this way, we see that, okay, they do seem, in some dimensions, they do seem to behave quite linearly. So it would be quite a logical, straightforward next step to cast them in a sort of linear empirical model to predict the performance of our device at certain operating conditions. This is exactly what we did. We tried to cast all of these data into one model using 3 main input parameters. One is the air injector stiffness, represented by the A3.1 over A3.2 area ratio, then the outlet throat restriction by the A8 over A3.2 area ratio, and the power throughput in the combustor, represented by the mass flux in the annulus. And using a whole data set, we then use this to train the model, and we arrived at this set of coefficients here. And using these coefficients, for our data, we achieve an R² value of about above 95% with quite good residual values. And then I went ahead and applied the same model to a different data set, this time from the Naval Postgraduate School. And we saw quite similar residuals for data that was within the parameter range for which the model was trained. Slightly worse for extrapolated data, but overall, even with the simple model, we achieved quite good results. What we can then do is go ahead and use this model and predict operating points where we would expect with this design positive pressure gain. So, for example, our best performing case, which was for a quite open area air injector at a 50% outlet restriction, we have about -8, -9%. We transform this point back to the plane of area, a normalized area, so A8 and A3.1. And in this plane, we also plot the one-to-one line, which we really do not want to cross, as we expect quite adverse behavior from our RDC to the right of this line. So from the output from our model then provides lines of constant pressure gain. And we have here the zero threshold. So everything to the right of this solid black line is associated with positive pressure gain at the highest mass flux value that we can achieve in our facility. And really this leaves only a very tiny design space here. And looking at these values would result in a very open air injector with a quite significant outlet restriction. So yeah, depending on the design and the device type, is really doesn't leave a lot of area to play with. What we can also do is use the model to predict the mass flux at which positive pressure gain would be achieved. And in our case, this would be a more than 50% increase from our highest value that we can achieve so far. However, the model is simple enough that it can also be extended with other parameters. What we thought of was, for example, the fuel injector or mixing performance based on, again, the area ratio of the fuel injector or the annulus aspect ratio defined as the gap width of the annulus to the outer diameter or some reference diameter, as well as the surface power density that takes into account not just the mass flux, but also the type of fuel and the stoichiometry of the mixture itself. And then we tried different combinations of these model terms, and they all seem to kind of give us residual values in the same range. So the R² value was typically above 90%. And really the benefit here is that the model is simple enough that it can be applied by any research group. And I would invite all of you to go ahead and take your data and use the model to see what you can learn about your combustor or suggest additional terms or other formulations. Okay, so now on to our last part for today, which really deals more with the gas turbine integration side. At some point, we extended our combustor by quite a bit to incorporate a set of nozzle guide vanes. These are very generic vanes, and what we were interested in, or what we are interested in, is how these individual elements, so not a blunt restriction that is uniform across the entire annulus. What would happen if we just place individual blocking elements in the flow path? How does that affect the detonation wave? Is the combustion process, the detonation process affected? And what do these effects look like? What we based this on were very generic guide vane designs based on the NACA 0006 airfoil. And due to their aspect ratio, they tend to be quite long. And we placed a total of 18 of these vanes in the flow path. They are just attached by 2 pins, but this also allows them to rotate them around a bit. So we were able to have them at an inclination of negative 8.6 or plus 8.6 degrees. And looking at this little sketch here, you can kind of think about that the detonation wave, okay, it can travel in one of two directions, but the alignment of the detonation wave and the oblique shock for these three cases is quite significantly different. And this is one of the first things that we looked at. We tried to determine whether there was actually a preferential wave direction for these three cases. In order to do that, we ran the same case, which is known to provide a pretty stable, steady single wave. We ran that hundreds or even thousands of times with the same configuration, but at different inclination angles of these vane elements. And then we took the time traces for each run of just two pressure sensors close to the detonation zone, and just did a cross correlation, so an automated process where we determine, we cut up the whole time trace into individual segments. And for each segment, we determine the correlation coefficient, which would give us the lag between the two signals. And across the whole range of runs, we can then plot a sort of histogram of these correlation coefficients. And this would immediately let us determine the wave direction. So of course, the blue sensor in this example is seeing the detonation wave a couple of milliseconds before the yellow sensor. So the detonation wave has to travel in a certain way. And indeed, when we compare now the whole data set, we see that for different vane inclination angles, one direction is actually more likely than the other. This is visible in the probability density or also in the cumulative distribution. And it's different enough that it's statistically significant. So we can actually say, okay, a configuration that has the vanes inclined at positive 8.6 degrees will be more likely to exhibit a counterclockwise wave propagation. Now, counterclockwise plus negative, positive, negative 8.6. This is kind of hard to deal with. So from now on, we're going to talk about a misaligned or an aligned configuration. And also this table is not really very explanatory. So we're going to look at it in a little sketch again. In the aligned configuration, we have the oblique shock wave oriented in such a way that it is more, I would say, normal to the axial chord of the vane profile. So more normal, arriving in a more normal orientation at the vane leading edge, whereas in the misaligned configuration, it's the other way around. And our hypothesis then is that because there is more energy reflected back in the misaligned configuration, the system tends to stabilize exactly in the other way, so in this aligned configuration. Okay, now we know that there is a preference, there is a preferred alignment. What does that imply for the flow conditioning across the guide vane stage? In order to find that out, we produced also a set of instrumented guide vanes that have either a keel shroud at the leading edge. So this is again a pitot tube in a keel shroud, and then this will have a capillary tube extending all the way to the trailing edge and then back out to a pressure sensor. Additionally, we also have static pressure ports distributed across the vane surface at these locations. So slightly upstream of the throat, exactly at the throat, and downstream of the throat. So we have access now to total or stagnation pressure data from the leading edge and the trailing edge. At the trailing edge, we can simply put our L-shaped keel probe, as we have seen before in the flow. And we also have access to static pressure along the vane, along the guide vane flow path. And the flow conditioning, that we can then compare that to isentropic relations. So from the measured static and stagnation pressure, we can back out a Mach number of the flow at that location. And compare that to a nozzle with a similar contraction expansion ratio. And indeed, we are quite close to so with our measured Mach numbers, we are quite close to the isentropically calculated Mach numbers. which is promising, and also underlines that the keel probe method can really be adapted for a whole range of combustor configurations and unlock some insights into the flow field. Similarly, the pressure distribution, so this is now the static pressure distribution in this vane, guide vane channel. This also follows the Mach number relation. So we have a distribution of Mach numbers based on the areas, and this corresponds to the static pressure in this relation. And using our data and comparing that to the isentropically calculated pressure distribution, this would be the dashed line in this plot, we are again quite close to that. Finally, we also see that the alignment of the wave with our guide vane elements has some implications for certain performance metrics that we defined for the flow conditioning. We see that the detonation wave speed, so here the plots are color-coded between aligned and misaligned configurations with yellow and blue. And we see that the detonation wave speed on average is slightly lower for the misaligned configuration, whereas for a configuration where we don't have any vane inclination, these are basically identical. A similar thing can be observed for the converted stagnation pressure. So this is the delta P of stagnation pressure between leading edge and trailing edge normalized by the leading edge value. And this in turn also has the same effect for the Mach number. So the Mach number difference, so the flow acceleration, will be slightly better for the aligned configurations. And lastly, we also see this difference in the surface pressure between, so the difference the delta between pressure side and suction side of the vane surface upstream of the throat. We have for the aligned configuration quite a significant increase in this pressure difference. Downstream of the throat, it's a different topic, but then the flow is already accelerated. So to kind of sum everything up, of course, there is no magic way to easily implement or integrate an RDE with a gas turbine, and the highly coupled nature of these devices really requires one to always consider the whole picture. We do have taken some first steps towards integration though, and we created some tools, for example, the keel probe method or the empirical model that can help in finding designs that are more conducive for integration. And we were actually able to predict the performance of the guide vane combustor quite nicely with the empirical model that was trained just on this bluff body outlet, this uniform restriction. Of course, the unsteadiness still needs to be accounted for in the flow. And what we have seen so far is that there is quite an impact of the wave alignment with respect to the vane inclination that also mode control strategies really need to be taken into consideration. Yeah, so main contributions of this work were the validation and implementation of a stagnation pressure measurement technique based on flow probes, keel probes, and we've also shown that there's quite good agreement with either the NPS method, so the Mach corrected CTAP, or the EAP thrust measurement. We've again provided some tools for assessing RTC performance and predicting design corridors, design avenues that might lead to better performing designs, and also towards turbomachinery integration. So my final words would be that despite some challenges, there is quite a positive outlook. And finally, I want to also acknowledge and thank my collaborators and the whole chair of pressure gain combustion at TU Berlin, which is at this point consists of Professor Miles Bohan, myself, Hongyi Wei, Florence Barnois, Tim Kaiser, and Roman Klopsch, but of course there are also countless other students, collaborators who helped in putting all of this together. And with that, I am done for now, and I'm open to questions. Thank you.
Hey. Yeah, thank you, Eric, for your nice presentation. Yeah, now the floor is open for questions. Please feel free to type your question in the chat, or you just raise your hand, or just directly open your video and the microphone to ask. Maybe in the meantime, I have one question relatively regarding this high-level part of this turbo machinery integration. I'm wondering, like, what is is there any material issues, like with this shockwave interacting with the vanes, or if you run it for a long time continuously, is there any structural or material issues that you see in this technology?
So we have not run it to failure.
Okay.
Typically, our runs are limited to about 1 second, I would say, so not really very long. Usually because we see that the device will settle into a certain operating point, and then there's not really a big point to extending the runtime, because we don't really learn all that much new stuff. But so our guide vanes, they are made from simple stainless steel. We actually make them in-house, except for the instrumented ones. These are made from a cobalt chromium alloy. They hold up quite nicely. So I've really used them on thousands of runs, and apart from some discoloring, they keep their shape quite nicely. Even we have pretty sharp leading edges. Yeah, they have not ablated so far, but I'm certain once you run it long enough, you'll be able to destroy it.
Right, but maybe a follow-up question is, if well, like for gas turbine, for energy, for like electricity generation, definitely one big requirement is the continuous and the steadiness, right? So like, what is the outlook for how RDE or RDC will be used for this, as it cannot really run for a long time due to all this material and structural reasons? Is it used like periodically, or like a complementary combustor to the conventional combustors?
Well, I know there's certainly a lot of research directed at dealing with this unsteadiness, also from a turbomachinery point of view. Even with our very unoptimized generic guide vanes, we've seen sort of, well, how to put it? So an attenuation of, let's say, of the amplitude, for example, of the static pressure variation of about 80%. So quite significantly. And I'm certain that you can come up with a lot more, a lot better and more clever designs to deal with this unsteadiness, and maybe even looking at things like supersonic turbines. But I'm not an expert there. As for the path forward, I think there are certain applications where it's much easier to integrate than for these, big, large frame stationary gas turbines. So I could absolutely envision something like single-use applications. Yeah, but as I said, the benefit even exists for lower turbine inlet temperatures, where you can use a lot of dilution air, and for especially for systems that operate at a lower pressure ratio, so microgas turbines going in that direction, and these can be, quite simple designs. So yeah, I think from my point of view, it's probably going to be somewhat of a step-by-step process, and I don't think we'll be able to integrate with an aviation gas turbine, but with simpler designs for sure.
Okay, I see. Thank you for the answer. I see Jackson has his hands up. Yeah, please go ahead, Jackson.
Thanks. Thanks for really nice work. I think it's important to do this careful characterization of the performance parameters. I have two questions. One's pretty technical and one's not as much. So on your slide 16, you compare the equivalent or the EAP to the two different pressure measurements. But you don't compare the two pressure measurements to each other. And it looks just from just looking at it by eye that the two pressure measurements are very close to each other. Can you comment on that?
They are, because they were recorded simultaneously. It's from the same data set. So there we were able to really put the kill probe simultaneous with the CTAP probe. So they do tend to be quite close together there. The EAP data set was recorded at a later time, and we had to do some corrections or some conditioning to be able to plot that on a really apples to apples comparison here. Because this is looking at quite a wide operating range, so wide mass flow range and also different combustor designs. What we don't want to do is have the kill probe at the same time as we do the kill probe measurement simultaneous with the thrust measurements, because this will of course have some implications for the thrust value and introduce additional blockage for sure.
Do you have a sense of whether the scatter in the data is more from the run-to-run variability or the instrumentation variability?
I would say it's not so much the run-to-run variability, but it's the fidelity of the whole measurement chain. For EAP, you really do need to incorporate such a wide host of really a lot of diagnostics, a lot of instrumentation. And to do it right, to do it with high confidence, requires quite a bit of work. And we certainly are not at the perfect value already. So there's still some elements that need some fine tuning.
Thanks.
It's hard. It's hard. I mean, that's the attractive thing about the CTAP or the kill probe method. For the CTAP method, I think now we're also, or the trend is also to use not one sensor location but multiple, and then kind of bring them together into one plenum to kind of have this pre-averaging of the data. But for the kill probe, really, you put it there, you stick it in wherever location in your flow path you want, and then you can directly get some data. This is a very pragmatic way of getting this.
Thanks.
Insight.
So my second question is that I know that you had this nice green text on your last slide, but looking at slide 21, which was the result of your model, and also just looking at sort of all the actual pressure gain data, the outlook to me looks quite bleak. Can you comment on that and specific, I mean, besides the small blue triangle, specific pathways to really achieve the potential that you showed in your first or second slide?
Yeah, well, I'm more optimistic then, because we have to kind of remember that this whole model, all of like this whole prediction is based on this combustor, and this is really quite an outdated old design. I would say it's more of academic interest than of practical interest. You have this really the worst kind of air injector that you can come up with, where you have to turn the flow 90 degrees and you really create a lot of pressure loss. So there's certainly much more clever ways to design the whole flow path in such a way that it does not impose such a big pressure loss that you invest for mixing and reactant injection. So yeah, I would say it does not look positive for this design, but there are certainly much better designs where you can get there easier and quicker. And
Okay.
I mean, we can still use this like brute force method and just put so many reactants in there that we get there eventually. But yeah, we want to be more clever, more intelligent. Yeah.
Okay, thanks.
Thank you very much for your question. Are there any other questions from the audience? Okay, I've got just one quick question, or maybe two. I was wondering if there was a choke that you had in front of your turbine blades.
No, well, what what you impose is this kind of converging, diverging channel with this nozzle, with this guide vane section. But there is no, so there will be a choke at the throat location there, of course, based on the airfoil shape. But apart from that, there should be no additional choke, no. But of course, this is not super representative of an actual turbomachinery architecture, since there'd be a blade stage downstream of the vane stage, of course. So what we are looking at also is ways to impose a certain degree of back pressure behind the vane stage, and what kind of implications that would have. I don't know if that answers your question, but
Oh, that's good.
So there should certainly be a choke at the throat location here. Yeah.
Right. Yeah. Just wondering if there was one ahead. And then my second question is, do you notice that or when you look at the type of wave structure that you have, counter rotating waves to co-propagating waves, how long does that last? Is it really steady throughout the run of your engine, or do you see it fluctuating in one run?
Not really. We haven't really observed too many mode changes in this combustor. Typically, it takes about, say, 150 milliseconds to sort of stabilize, to find an equilibrium where it likes to sit at a given condition. And that we don't really see much change in there then. So the longest run I've seen was about 10 seconds, and this was very steady throughout the whole run. So yeah, it likes to find an equilibrium and stay there. Also stuff like wave reversals that other people have reported on, I have not seen in this device. Yeah.
Thank you very much. Are there any other questions from the audience? See one hand up.
Morning. Lovely stuff, Eric.
Fabien? Yeah.
I was a bit late there, but I just wanted to ask if, and I may have missed it, if y'all ever did any characterization of your Q probe response times. See what they might be.
Response time. So I mean, yeah, we did. Let's see if I can pull this up. So maybe you can see it here. What we did is we put our kill probe behind a small shock tube and just hit it with yeah, so, different velocity shocks. And what we see is that from the information arriving at the probe inlet to when we record it with the pressure sensor, that corresponds quite well to the yeah, just an acoustic oscillation, so propagating at speed of sound in the internal capillary. What I also tried is to do some acoustic forcing, but this of course has much smaller amplitude. And the frequency response was, yeah, I would say quite flat. So there's no resonance or anything in this design. But then the capillary, the standoff distance is about 150 millimeters from the probe inlet to where the pressure sensor sits. Yeah.
Gotcha.
Yeah.
All right. Thank you.
We looked at it. We didn't see too much attenuation. I would say between 5 to 7% for the worst case. Yeah.
Lovely. Thank you.
Yeah, good to hear from you, Fabian.
Yeah, always good to hear from y'all. I see that y'all also fixed the material rearrangement problem you
No.
told us back in the day.
Yeah, that was the very first design.
Well, thank you.
Okay, are there any other questions from the audience? If not, Eric, I'd like to thank you again, or thank you for the first time, Zacheng. Thank you previously for coming and participating in the Young Researchers Forum, and also for everyone who showed up today. So thank you, and we'll see everybody next week, I hope. Yep. Bye.
Thank you. Bye.